welcome anyways at Stanford and quickly introduce myself. I'm originally from Belgium. I got my PhD in mining engineering at that time, and I came to Stanford in '97, right after my PhD, and I got hired here. So I've been here for quite a while. I did a stint for a long time in petroleum engineering because mining engineering wasn't popular at that time. And then this year I decided that's enough of that and go back to minerals because critical minerals is going to be a very important part of the energy transition. I'm also a key data science and AI advisor of Cobalt Metals, and I'll talk about Cobalt Metals as a startup company that went from, in the last 4 years, from 10 employees to 100 employees and owning a mine in Zambia. I'll be traveling to Zambia actually in a couple of weeks. But beyond that, I also talk a lot about general energy transition. So masterclass outline, we're going to think very structured. As was said, I'm also a mathematician, so I like to define things, and then I like to formulate things, and then I like to solve the formulations. And that's always been some of my viewpoints. So we're going to look at the key ingredients of what is energy transition, what does it mean, and how can we actually think about that in a very formulaic way. And then, of course, we want to solve it, right? We want to do things. So let's talk about energy transition. And let's just say, for fun, that we want to get 100% renewable energy. Okay, what does that take, right? It's going to have ingredients, and what are those ingredients going to be? And there are 4 main ingredients to that. And number 1, as we all know, is wind and solar. Then we need water. Hydropower is a big thing, right? Brazil, as electricity, 85% is hydro. We want to use the Earth's heat for geothermal, and that could be shallow geothermal or very deep geothermal. And we need Earth's minerals for batteries and for other types of devices. And we'll see what minerals are very important. We also need technology, right? And that's often what you're here for. You're here doing a PhD. And if you're in engineering, you're going to develop technology. And so what do people think about technology related to the energy transition? And there are many thoughts about that. But here I'm going to put 2 up, which is 2 books or 2 documents that appear 2 months apart. One is by Mark Jacobson, who's a professor here in civil engineering. And he says, we have all the technology. No miracles needed. We just need to refine the technology. We need to combine technology. But, we don't need fusion or we don't need any of those things to make that happen, okay? And he writes that in this book. Now, a couple of months later, Tesla comes out with say what is needed for the energy transition, and they're saying the same thing as Mark Jacobson. There's no new technology needed. The only thing that Tesla does different is nuclear, right? So they do more nuclear. Mark is very anti-nuclear, so he doesn't have that in his portfolio, okay? So for technology, we could almost say everything is there. The battery, the solar panels and things like that. Okay, so we need, of course, more than that. We need policies, we need actions, we need to do things. So let me go over some examples of this technology and why, in the end, we're going to have to use artificial intelligence to solve the problem of the energy transition, in my view. The number 1 technology that is not talked about a lot is shallow geothermal energy. Right? It's energy that basically sits right under our feet, where there's a constant temperature in the subsurface, and that constant temperature allows us to exchange heat, right? Cooling in the winter, cooling in the summer, heating in the winter. Now, in this area here in China, the Tri-City area, there are 235 million people. All those million people, they essentially heat themselves using electricity. A stove plugged in. There is no distributed heating in these cities like we have, right? That electricity is generated by burning coal. Okay, so that is like a no-brainer for let's transition. So what does this transition then look like? It's actually quite simple technology. It's technology that says, let's put some pipes in the subsurface, let's circulate fluids, heat exchange, and we can cool buildings, right? That's the heat pump, we call that. That's a very old technology, and that has amazing applications. Now, the problem with that is that doesn't work everywhere. It only works in the areas where you have a temperature gradient and when there's enough groundwater flow for us to do that. Okay? And so therefore, people go and make, using satellite information and remote sensing information and geophysical information, they make sort of maps of where is the heat potential in China for shallow geothermal. And then you see, well, there's a lot of heat potential. But the maps they were making here often, and we'll see the steam is coming back, is these maps are very, very low resolution. They're very global scale, very low resolution, right? So even if you would go in Shanghai, you will find that in the subsurface that heat is not uniformly distributed. It's very heterogeneously distributed. So then the question is, if I want to do that, right, now I want to say, that sounds like a good idea, sounds like a good technology, let's do it. Well, I will have to take measurements, right? I have to start measuring where this is the potential actually can be achieved. And then I have to invest in deploying this technology, and that investment, somebody has to pay for that investment. Right? And that is the challenge. Often with renewable energy is there's good ideas, there are good technology, but we don't know exactly whether they're going to work in the situation that we are. We need measurements. What kind of measurements would we take? Right? That the technology doesn't say that. So these are kind of questions I'm interested in. Another area, a very different city altogether that I work on is in Vienna. Vienna, they have a very deep geothermal energy. Because Vienna is a basin, actually there's an oil and gas basin, and people pump oil out there, but at the same time, we're going to do this distributed district heating. So again, it's an exchanger with the groundwater system, but this groundwater system sits very deep. It sits at like 80, 90 degrees, which is good for shallow geothermal. If you want to do actual electricity-based geothermal, you would have to go to 150 degrees centigrade. But that's good enough there. Okay, so what do? A company called OMV, which is actually an oil company, wants to go into renewables and say, well, oil and geothermal is very similar. You have to drill, you have to inject fluids. And so we're going to inject fluids into this subsurface, and here's a model of the subsurface, and you see here the temperature. And in that temperature, you see that indeed you have some area, right? This is too deep to drill, it's too costly. That's another problem of geothermal, is that drilling is expensive, right? And so you have to, again, this is an economic problem, so we're going to go drill a little less. And then we inject cold water, and we pump up, you see there's two wells, right? There's a duplex. We pump up the hot water, and that allows us to heat things in the winter. So that's a great idea. Now, if you look very carefully, you see these things here, right? Those are faults. Like we have the big fault over there. It's called the San Andreas Fault. You know, you're not far from this thing, right? It's right at the 280 freeway. It's right there, okay? So if I take a binocular, I could see it from here. So faults. So what's going to happen when you put fluids in a fault? Earthquakes. This is an earthquake in South Korea that happened not that long ago, which is not due to plate tectonics, it's due to geothermal energy production. Okay? So the people in Vienna, they are looking at this video and they're saying, wait, you're going to pump fluids in the subsurface and there are faults? Okay, so this is a safety issue, it's a safety critical issue. Right? A lot of this, some of the renewable energy in the energy transition, we're going to have to deal with safety critical issues, particularly when you're dealing with the subsurface. So what happens is that you pump water in the subsurface and that changes the stress field around the fault. That makes the fault slip, which creates the earthquake. And a 5.4 earthquake is going to kill, of course, geothermal energy in Vienna, and then we have to keep gas, right? There's another, in the energy transition, a lot of people talk about carbon capture and sequestration or utilization of the carbon that's being captured. And that is often recommended for hard-to-abate industries, particularly steel and cement. So we would capture the CO2 from burning and then we put it underground. Okay, now this is the geological storage of carbon dioxide. Now here we have a double jeopardy. Double jeopardy is that you have the same problem here, the fault, right? The CO2 is not a gas, it's a liquid, and that can cause earthquakes. But then you have another one, which is actually much more problematic, which is leakage of CO2 to the surface, Right? And so the problem with the leakages is this very hard to measure that it's going to leak, because it may leak in 1,000 years, right? But the people that put the CO2 underground are no longer around in 1,000 years. So who's responsible for this? So leakage is a big problem for that, and measuring that and regulatory frameworks for that are important. So yes, you see, we can have these ideas of mitigating the greenhouse gas emissions, but there are, again, safety critical issues related to this. Last example is that I work on a lot, is that of the circular material economy. That means we are going to mine things, particular minerals, then we're going to use those minerals in appliances or cars, and then we're going to recycle those minerals, and then we're going to reuse them, and so we go create this circular economy, right? So recycling is actually, we know how to do that, it's just very expensive. Recycling lithium is very expensive. Copper is already recycled 80% in the world, so copper is really up there. So there are, in a car, batteries. We have typically a number of types of batteries, right? You have the nickel cobalt battery, you have the iron phosphate battery, but all the batteries that are going to be here in the next 10 to 15 years are going to have lithium. Right? So it's unlikely that sodium is going to have an application in a car simply because it's too heavy and doesn't have the energy density. Right? So for cars, this is a big thing. The other thing that is very critical is copper. Right? Copper, if you're going to electrify the world, we're going to need a lot of copper. How much more? 5 times more of that and 3 times more of that than we know there exists. That means there isn't even enough. We know it's there. There's enough lithium and copper in the world, in the crust, to power trillions of vehicles. But there are 2 problems with that. Number one, you have to find it, right? And then the second thing is they have to make sure you can extract it economically. It has to be at a sufficient concentration. So there are very insufficient amounts of these. Particularly lithium, we're thinking that the crunch will happen around 2030. And for copper, the crunch will happen around 2035. That's not that far away. Okay? And the problem with discovery of minerals, and this is what I work on, that it takes, and we'll talk a little bit about that, once you discover, it takes, in the United States, about 15 years to start a mine. 15 years from now, that's way beyond 2035. Right? So there's an issue just with permitting and social license and all kind of things like that. Okay. So, I've just given you a bunch of examples, and you can come up with more examples. In the end, I will talk about more examples, and you can imagine in your head you have other examples of the energy transition. And so now the question is, can we formulate this problem? Because if you can formulate the problem, then we can use solutions that can be reused time after time. So that means I can use that solution for geothermal energy, or for batteries, or for whatever else I want to do. I can reuse that. So we have to think carefully about this. I'm going to show it with an example, but this example is just one example, right? At the end, I will talk about that all the other examples apply equally. So if I decide, for example, to do carbon sequestration, that means I have to inject into the subsurface a fluid, right? And hopefully that fluid here stays at some area. Under a rock that is impermeable. Right? And that's what they try to do. Now, in reality, I don't know exactly what the rock looks like, right? It's in the subsurface, it's far down, I don't really exactly where it is. So we have a lot of uncertainty around that system. Then, in order for me to mitigate this uncertainty, I need to take observations, right? I'm going to take data. Data could be lab data, could be field data, could be remote sensing data. You are going to use data. And at the end, right, after so many years, I want to achieve something, which is called in AI a reward. I want to inject as much as possible, but I want this to not cause any earthquakes, and I want it to cause not any leakage. Right? Those are rewards. Okay, so now I've mentioned 4 things. Okay, so that's what we're trying to do here. This is just a cartoon example. I'll show a real example later on. right? Is you have a fault on each side and you're injecting. So your question is, where do we inject? Right? Do I inject in the left or the right or in the middle? And then how do I monitor such that it doesn't leak? It means I have to have sensors, maybe at the surface, maybe in the subsurface, that monitor the whole system, right? And you can say, let's monitor the hell out of this, right? Well, that's expensive. So then you have the economical part, right? And you have to do this for how long? Decades and so on. Right? So these are questions that we're trying to answer. So you see here, you also have the uncertainty, right? You see that the surface is very uncertain. That's why you have this ensemble of surfaces, right? Because we don't know perfectly where the surface is, except where we drill, right? We know there's the surface, but otherwise it's uncertain. And I don't measure the surface indirectly. What I can measure, for example, using seismic data, I can measure the saturation, where it is. Okay? And so here's the solution. It says drill over here, inject here, and then here you see these blue arrows. That's sense, measure. That's literally, those are sensors at the surface. These are called geophones. They listen to what's in the subsurface. When a fluid moves, there's a little noise made, and that can be picked up. Okay? But these sensors are imperfect. They're not perfect sensors. Right? They can make mistakes. There are errors related to that. And at the end, I want to have a reward, right, where everything is trapped and nothing is exited. That's what I want. Okay, so 4 major components in all energy transition problems. We want to achieve something. You want to achieve something. A reward. And that reward could be multifaceted, right? Of course, can be short-term, can be long-term. For example, in the long term, you want to get net zero. That's a reward. Right? You can also say, I was talking to a person from Microsoft, and she says, well, I really want to start doing things today. What can I do? And I say, well, it's not independent necessarily of what you want to do in the long term. So you have short-term rewards, you have long-term rewards. Okay, we're all on board with that. We're going to do engineering. We're going to take actions in the real world, right? This is not a mental thing. We're going to be drilling wells. We're going to build infrastructure. You're going to do things. You're going to make pipelines, actions. However, there's lots of uncertainty. There's not just uncertainty in let's say, the subsurface. There's also uncertainty in economics. There's uncertainty in supply chain uncertainty, right? There's uncertainty in every aspect that's going to happen in the future. So we can have and describe that uncertainty with probability models, and we call that in AI, we call that belief. Okay, that's just a short word for probability density function in a way. And then we have observations. We're going in the future, right? We're going to measure things, and they are going to come together to help us with reducing that uncertainty. But there's more than that. There is time and space. We're going to do things over time. Okay? Not everything gets decided today. We're not going to say, you're going to do your PhDs, and we're all coming up with a plan, and we execute, and then we go on vacation, right? We're not doing it that way. Right? Because why? Because we know we need to be able to adapt plans, and we are getting, in the future, information. Okay? So think about this problem as a chess playing problem. You're going to play chess. How do you play chess? You don't play chess by telling, I'm going to make my moves now and then go on vacation, right? It's not like that. I'm going to make, and the other thing you don't do is you're going to make one move at a time and forgetting about what else can happen later on the board, right? Because later you're going to get information, which is the moves made by your opponent. So good chess players, in their mind, they can move 6, 7, 8, 9, 10 steps ahead. That's what makes them good chess players. So how can we formulate a problem like that? This is essentially a sequential planning problem or a sequential decision problem with uncertainty into it. So we're saying here that requires understanding this decision problem, and decision problems are understood through decision science, but also through artificial intelligence. One part of artificial intelligence is, in fact, decision science. That is, how do you decide? If you think about artificial intelligence, you think probably about ChatGPT, right? And it's almost like if you're not doing artificial intelligence today, there's something wrong with you. Right? That's not the case. So ChatGPT is not a decision maker. ChatGPT is a predictor or a generator, right? So we're thinking, and we'll show that in a bit, we're thinking about an AI that sits on top of all of that, that can reason, that can act, can decide in the real world. To do that, we have to formulate this problem, and here you see a formulation which is called a dynamic decision model. It says that if you take an action, this is time, okay? This is time. You take an action, you're going to get an observation, right? You're going to drill a well in the subsurface, suddenly you get an observation of what is along the wellbore, right? That is one example, but there are many other examples. If you take an action, that's going to then also result in a reward, right? When you drill a well, you start pumping fluids or you start injecting, you get heat, that is your reward. However, that reward is not certain today because we have uncertainty in the subsurface. So we have to make predictions of that reward. And that predictions is used the belief that we currently have, right? And so that belief, once I have that, I can now use the observation to update that belief, to change the belief into a new belief, which is called BT plus 1. Okay? So this is a dynamic decision model that captures most actions, observations, rewards that you can imagine. Okay. I have only one slide with equations because I want to show that there is math behind this. Okay, no, I have no equations yet. I'm going to show that this decision dynamic here is the same as a robot and a sensor. This is also where this AI comes from. This AI is developed in the robotics world. Is also, if you flew here to San Francisco Airport, I used AI, that's called ACAS, which is an aircraft collision avoidance system that uses this same AI. It uses this decision framework. Okay? It's not an if-then-else AI, right? It's not like if this plane is that and I'm like that, then I should stay like that. That's one move at a time, right? That's called an expert system. People don't use that anymore. That's all replaced by this kind of system. So what is a robot? Say, imagine you have a triangle there, and you want to move it over here. You want to pick it up and move it over there. How would you do that? Right? The number one thing that we have to know is that our sensors are not perfect. Right? Suppose you have a poor sensor, then instead of having this exact state, S, the position of your triangle, you have the belief over that state, B of S, the possible positions. Then it needs to pick that up and move it. Now, when it moves it, this thing here is not perfect either. That means you think you move it over there, but in reality, it had moved it a little bit to the side. It didn't quite execute what you wanted to do. It's the same with a plane that's flying. If the pilot says, go up, then that may not happen immediately, and there may be delays and so on. So there's another uncertainty, which is called transition uncertainty. Right? There's one that's called observation uncertainty. Another is called transition uncertainty. And then you have to keep doing that, and so on, right? Then you observe again, and you keep doing that until end. So the equations, and this is what I want to show, and I'm going to not talk about this at all, but I'm going to show their equations, are the three equations that govern this AI. And these equations are about, you need to make a decision based on a reward, right? And that reward is uncertain. So that's why we have this uncertainty in here. Okay? Then you're going to make observations, and observations are going to change uncertainties. So if you have heard about Bayes' rule, then that is here Bayes' rule, a little bit more complicated. So most artificial intelligence is Bayesian, as we say. We'll see later that's going to be important, particularly for the minerals. And then you have transition, right? You're going to transition the system, and that's Markov. Means you go from one step to the next step to the next step, right? And your next step doesn't worry about the history. It only worries about the previous step. That is the Markov. So we call this formulation of the problem a partially observable, right? Not perfectly observable system, Markov decision process. So all of these examples of the energy transition are POM-DPs. The solution of a POM-DP, if you solve it, and we'll solve that in a bit, is called a policy. A policy says that if you are in this state, then this is the action you should be taking. That's the answer, right? So if in the future you find yourself in this state, you have to then take this action. It will tell you that. The interesting part of this POMDP is, and this is what I found very counterintuitive, is that future information changes the current action. The current decision you make is in fact dependent on information you'll get in the future. There's a feedback between future information and the current action. If you're doing optimization under uncertainty, closed loop optimization, any course you take on optimization ignores that information effect. And that is the breakthrough that AI has. It uses future information to improve your current decision in a very complex feedback system. So that's great. That's a nice formulation. Equations, but equations don't do anything unless you solve them. So how can I find this here, this policy? Okay. So in order to do that, I'm going to implement a solver, and a very common solver is called a Monte Carlo tree search solver. This is the solver implemented by DeepMind, AlphaGo, the Google company, right? To beat every single chess player, every single Go player. If you're on your phone and you put the setting on, as good as possible, you will never beat the machine. The machine will always beat you. Okay. And it's kind of interesting because you may have heard this news about, I'm a little in the chess world. Anyone here play chess and follow the chess things? You know about the scandal? So the scandal about this guy playing, what's his name? Magnus Carlsen, yes. Magnus Carlsen. And so Magnus Carlsen suddenly quit, and he says he's cheating. And it turned out he was cheating. And the reason he found that out is that the solutions the computer gave were completely counterintuitive than any human would ever do. That was the reason why. Okay? There was actually a move where in the second move or third move, they gave up their queen. Right? That's not something you would be doing unless you had right? You can think 12 moves ahead, 30 moves ahead. So here we see that in order to solve this problem, you can understand that there are essentially two curses. The one is the curse of dimensionality, is that your action and state space is very high dimensional, we call that, right? Is that problems particularly in the Earth, are very high dimensional, complex. You need a lot of parameters to describe that. There are many possible actions and combinations of actions possible. And then you have the curse of history. And that's to do with the data. There are many combinations of data and actions possible as you roll out the future. So here, the computer is rolling out the future of the board and testing all kinds of possibilities. The contribution of the Monte Carlo tree search is that it can find arms in this thing here that are very promising and walk back those arms and thereby optimizing the system. So that is how that particular tool works. And this is at the foundation of most of these AI systems, is these kind of Monte Carlo tree search solvers. Okay, so if you now apply that to our little toy problem, remember the toy problem with the surfaces, right? Then we can do, there's a number of things we are comparing here. This is when you don't do uncertainty. You ignore uncertainty. This is when you do closed loop optimization. You optimize only one step at a time. You don't do the rollout that we saw in the tree. You just do one at a time. Your tree is one layer deep. Okay? And what we notice is that in all of these solutions, we always get leakage. Right? You could say, well, why didn't they detect that? Well, remember, you have to put your plan in today, right? Today you have to say, I'm going to put these detectors in, because you're in a real field. You have to buy the detectors, you have to install them, and then you have to walk away, and then they start injecting. Right? You can't so suddenly say, oh, stop, it's leaking, I put more detectors in. No, that's too late. Right? So no matter, if you don't account for this feedback of the history, you'll get leakage. And if you actually do that, this is the POMDP solution. There's no leakage. So you can then start applying that in the real world, and this is a real case in Eastern Europe. where we have what's called a depleted gas reservoir. This is a reservoir that has gas in it before, methane. It's depleted, and so lots of pore space. It's a really great case for CCS because you already had a gas and you're pumping something gaseous in again, and so that's really to your advantage. And so in a gas reservoir, you already have wells, and what you need to do is choose the location of the wells. Which wells are you going to inject in? The other thing is that you don't need injectors here. You can actually use one well to monitor the system. And here we have 18 wells. So the question is, which of those wells, how many of those, and which one is your detection, your monitoring well? And it should not leak, and you should get as much gas in as possible. You see, that's not a trivial problem. You can't solve that with optimization. Why? Because you get information in the future from the detection well. You get that information comes to you in 50 years, maybe. And that information is uncertain. We don't know what it's going to be. Okay? So here's the solution, is that those are the 3 wells you inject, and that is the one you observe. And then it fills in the whole thing, and that is your CO2. So we're looking from the top here, and the color is the CO2 saturation. Right? And this kind of potato chip kind of things that you see there, that's the surface. That's not certain. That surfaces are quite undulating. Real geological surfaces are not flat. They are quite undulating, right? And that's very important in order to do that. Okay, so you say, yeah, that seems like a very specific example, right? But it isn't. Now we're going to move to mineral exploration, and I'm going to use the exact same software. Don't change anything. Same solver, same formulation, same ingredients. Okay, so let's talk about mineral exploration, because it's close to my heart. So where do our minerals come from? They come from the subsurface. The problem today is that most minerals deposits that are outcropping at the surface have been discovered. So you're standing here in Palo Alto, and there's nothing at the surface except beautiful grass. How do I know there is a mineral deposit there? That's the world challenge right now, in order to get the minerals out. Okay? So mineral systems are typically created very deep from the earth, from the mantle. They're plumes that come up. They get concentrated into metals typically, and those metals react with the sulfur of the crust and make sulfides. That's just one way of doing that. Copper sulfides, nickel sulfides, cobalt sulfides, they are all part of this group of sulfides. And they get created in these chambers here. So it's like a pipe system, right? And sometimes you have this here, we call them the massive sulfide. That's what you want to be mining. Right? And so what we want to do in the world is find very high-grade deposits. If you have high-grade deposits, and this is like 100 meter of very high-grade nickel, you can just mine it through underground mining. You just drill a little thing and you start mining it out, literally like surgery, and you get it out. The problem in the world today is that, number one, they're hard to find, and that the existing mines today are all low-grade. And so what happens when you do low-grade mining? You're going to dig out all the earth around it. So, for example, there's a copper mine in Arizona that has 0.3% copper. That means that 99.7% of the material that's dug out is waste. Okay? And if you look at this mine, it is huge. It's a big hole in the ground. So we want to avoid that. Right? So we want to find these high-grade deposits, and that's really the role that I'm starting to play with this. How do you find mineral exploration? You start really from very big scale. Right? Here we're on the mid-continental rift, and people know in rift systems often we have these kind of fractures, and so we want to look there. Then people fly helicopters, and they measure magnetic field and gravitational field and all kind of geophysics. They land on an area where they think is kind of interesting, right? And then they go start eventually with drilling. But this is the expensive part. Flying a helicopter, putting loops on the ground. You could do that. You can go to the Lowe's and buy some stuff, and you can do it yourself, right? but this here, millions of dollars. Now, this is in Canada in nowhere. It's not like, oh, there's a road there, let's go drive there. You have to sometimes make your roads, okay? So this is, you see how difficult this is. So what we have developed with Cobalt is a really comprehensive system to start doing mineral exploration. So Cobalt was a company that became part of 4 years. There were 10 people. We're working on 2 assets. Now we are on 3 continents. We're working on 50 assets. And the reason why we do it is that we do it with AI and we do it fast. And nobody in the mining industry uses AI, period. You go to Rio Tinto, BHP, all these mining companies, they have Excel sheets or PDFs. That's like the technology that they are using in terms of, if I ask a mining company, can you give me data? They send me literally an Excel sheet, right? And then in the Excel sheet, they do their computations. Okay, well, how about Python? No, we haven't heard about that. Okay, so that is the level of sophistication. So we're coming here with this AI. So you see, this AI is going to use data, right? And this data ingestion, this is, all, of course, very big thing. And then you can do machine learning, which you call machine prospector, that can take data and make maps. Okay, so for example, you can take the data and can make a map like this that says, okay, there's an intrusion there, and it looks like you got some nickel potential. Okay, that's machine learning, but that doesn't decide you where to drill. Now we have to have an AI that can decide what is the next data I should acquire, and what is the next after that, and what's the next after that. Okay, so that was a sequence that I needed to decide for that. So why is it important? It's important because, and this is a graph that shows the exploration efficiency starting in 1990 to today for copper. The last major copper deposit was found 20 years ago. Okay, that's the situation. And the efficiency, the amount of dollars invested relative to the discoveries, has dropped 10 times. So companies have run out of ideas because everything at the surface has been found. Why is that? Well, in order to understand that, you have to think about this person here, Karl Popper. You know Karl Popper? Who knows Karl Popper? It's one of my heroes, scientific heroes. So Popper is the person that came up with the paradigm of falsification, right? Saying that in science, you can't prove anything. You can only disprove things. You can only falsify. What we're finding here, what we discovered with cobalt, is that a lot of things look like a deposit. Something shows up on a magnetometer, and people get super excited because, you know, metals have magnetic properties that are interesting, and then they drill into it and they find graphite. Right? So we call that false positive. So key to mineral exploration essentially is that you should not try to get what we call confirming evidence. A human loves that, right? I think there's something there, let me go find it and drill it. Right? This is very typical in mineral exploration. There are companies, they buy one property and then they try to find and confirm it. What we're doing with cobalt is try to falsify it immediately, is to try to get rid of it. And if you try to get rid of it, you're finding actually more deposits because you're much more critical about your own thinking. So our AI also uses this thing, and this is where cobalt really was put on the map, was last year at the US Africa Summit. Well, Cobalt became a mining company supported by the US government at a rate of $150 million investment in Zambia, in the Copper Belt. The Copper Belt is a huge area. It goes all the way to the Congo, which you may have heard of, right? This child labor mining kind of stuff. Zambia is a completely different country. Right? I'll be traveling there, and it's very democratic. People have really engaged with communities, etc. So what are we doing in Zambia? This is what we're doing in Zambia. You see, we're drilling, like, this is action, right? This is like real stuff. And this is just one, okay? One borehole. Now, if you look at the Copper Belt here, you see all these dots? Those are all boreholes. Okay, one borehole may be taking you a week. Okay, and then you have a number of drill bits and you can go around, but this is what the mining companies do today. They just punch the hell out of it. This takes years to do. So we came up with this idea of intelligent prospector, or the POM-DP solution to that. And what's the POM-DP solution look like? It looks like this. It's like a chessboard. This is how we drill. Very different. We don't drill everything at a time and then start to analyze it. We drill, we analyze, and our goal is not to confirm. Our goal is, as we said earlier, to reduce uncertainty. Often what drillers do is they try to find high grade. No, we try to find low grade, because that allows us to falsify. Right? So we don't drill in this pattern. We drill in this pattern. So that well that you saw earlier, that drill rig, right? That was using AI. That was put there in that fashion. Now, when you plan the first borehole, you don't wait for the second, the third. The first borehole is planned with the idea that you may have 12 more, or 13 more, or 20 more. Remember, that was the search tree that I saw, all the arms, right? That's that combinatorial. We figure out this combinatorial. We don't go just one step at a time. And in the end, this is a mock-up example. You want to know whether you are below or above a certain economic threshold for mining, right? That is the reward, is that you know this decision that you have to go walk away or go ahead and start building the mine or defining that. Okay, so that's where we are today. And so now we're thinking about, okay, now we got a machine, right? And we can use this machine for many things. Because all problems that are in the future, that are uncertain, where you will get observations and you have to make different actions, those are AI problems. So now we have working on what is called the lithium supply chain problem, where you have to think not just about exploring, you also have to think about mining and processing and manufacturing and recycling. And you have to think, how in time is all that going to take place? And where in the world is all of this going to take place? Now for lithium, it's actually quite complicated because there are three sources of lithium. There's a hard rock lithium, there's a brine lithium, that's the stuff that's in Chile, or there's clay lithium, that's the stuff that's in Nevada. Right? So you then have to think also about, mining companies have to think, what should I be mining? Should I be doing brines or should I be doing hard rocks? Right now, 50% of the world mining is in Australia for lithium and 40% is in Chile. So it's two countries. Luckily, they are friendly countries. Right? And the United States wants to also start doing lithium mining. But the question you can have is, for example, should they be doing that? Should we be doing that? Or should we be collaborating with Australia and Chile and get the lithium from there? Right? So what we are setting up here is an AI problem where these actions, choices, are modeled. And at the end, you want to get a reward. And the reward is quite complicated. You want to get your mining, you want it to be resilient, secure, right? Environmental, decarbonized, etc. So this is your reward at the end. So what are these actions? So one of the things we already know is that recycling is not going to happen until 2040. It has no effect. Right? And it's going to take a long time because we can have second and third lives of lithium batteries for storage. Another example that I'm working on, and will also be traveling after Zambia, we're traveling to Morocco, is working with a company called Travertine. It's a company in Colorado. And what did he work on? So on the top picture here, I'd like you to focus on that. That is see it's like a white mountain. That's not snow. That's phosphogypsum. This is an element that's the waste product of phosphate mining. And phosphate mining is done to get phosphorus, which is a fertilizer, right? 50% of the world production of phosphorus comes from one country, and that is Morocco. But you get that byproduct, the waste. This is a common thing, right? Is that we're building stuff, we're creating stuff, but then also we have waste stuff. So what do we do with this waste? And you say, well, isn't that nice mountains not a problem? It's a huge problem. There's uranium in there, there's rare earth elements, there's radium in there, there's all kind of stuff in there that you don't want, because under the thing, you see there's water. right? It was actually a year ago in Florida, one of those things collapsed into the groundwater system because there's karst under Florida. Everything collapsed into the groundwater system, a whole bunch of uranium and radium in the groundwater, and EPA said, yeah, it's fine. No, it's not fine, right? So what Travertine is doing, together with our sponsor, Bitra, which is a venture capital sponsor, is try to do a win-win situation. Is to try to use the waste as to create into a product that you can sell, right? One thing you can sell is, for example, cement or drywall, or you get the uranium out, or you get the rare earth elements out, right? The other nice thing that they're doing is that in order for me to create these carbonate minerals, I'm actually going to use carbon dioxide from the air. Okay, so I extract carbon dioxide from the air. I have this electrochemical process in which I also put the sulfate waste. So I have two wastes, right? Carbon dioxide from the air, the waste, phosphogypsum. I have an electrochemical process, and out come things that are products. Sulfuric acid, right? We need that for leaching. We get green hydrogen. We get all kinds of things that are useful. Now, you say, that's amazing technology. Let's do that, right? Well, where is the state of the art of this amazing technology? Is over here. About here, the size of this thing. So the question is, how do you upscale technology? The problem with upscaling technology when you're going to apply it in the real world is that you're going to meet variability of the real world. Right? The composition of that stack is not uniform, beautiful, the same thing. It's very heterogeneous. So you have uncertainty on the material. Then you need to build not just these things, you need to build an extra plant for mineral processing, and that plant requires decisions around sizes of things and how you're going to process that. Those are actions. In the end, you want reward. What is reward? You want to get these products, but you are also consuming energy, right? So you want to minimize energy and maximize product output, reward. That's an AI problem. Okay? Upscaling technology is an AI problem because you're going to go from the lab scale. A lot of you are going to be doing things like this, right? And you need to get to that mountain there. Right? You can't just scoop the mountain into the lab and make that work. It's going to take forever. So you have to build these facilities, and you have to also account for the variability. Okay, just a couple of things that I want to mention is that I'm also very interested in community building and stewardship. So a lot of our work is also in combination with the environmental justice groups here at Stanford, and I think that you have heard some of that as well. We're traveling to Morocco. Morocco is want to be at the center of Africa. I think Africa is a very important country to work with. We'll go with my student Sophia, and then also my postdoc Jonas works in the rainforest where there's a lot of mining and a lot of problems as well. If you want to have more information, I have a website called mineralx.stanford.edu. Otherwise, I'm happy to take any questions. Thank you. Yes.
Thank you very much for the talk. Very inspiring. I have a question about the data sets you used for training. These problems look to me to be so multidimensional that despite hundreds of years of mining, it's. I was really surprised that the data sets are enough to train them.
You can train the data sets to predict potential for a deposit. So you have, for example, you have all kind of geophysical data sets. They're exhaustive, they're very beautifully looking, and then you have drill holes that have been drilled in other areas. For example, you get the nickel grade, right? That gives you a map of potential. But as Popper says, lots of things look like potential, so you have a large false positive. Then you need to have that second AI, which is the one I talked to, with decision AI. That one you can't train because nobody has made these decisions before. Right? So it's not that I can look up in the history and say, what decisions did people make and how successful were they when I was drilling in such and such situation? So that does not exist, that type of data set. In a way, you have to create that data set. And the way we create that data set is through what we call inversion. We're taking geophysical data and we invert it into actual rock properties in 3D. But that inversion is very uncertain. So that's where we create essentially the data. You have to create them yourself through this inversion process.
Yeah. Thank you.
Yeah.
So could you go back to your slide that had all of the rewards towards at the very end of the modeling?
This one? Yeah.
So what I'm wondering is how you, I guess you have your formulation and everything, but what I'm wondering, how are you quantifying your reward for like resilience and social license, and how do you, I guess, how is that an effective reward?
Yeah, so number one is the quantification, and then second thing is the prediction of the reward, right? Quantification, you can use any kind of metric, but the question is, if you're taking a bunch of actions, because here you have a bunch of actions, right? You say, I'm starting to decrease China import, or I'm starting to implement mineral processing in Australia. Then you have to predict in time how that's going to evolve. So there are a number of things here, tools on this side, which we call dynamics. So one tool that we're going to use is material flow analysis. It's essentially seeing where in the world the material is flowing when you're thinking about lithium. So it could flow into the batteries, but then it goes through several countries or processes, right? The other thing is called system dynamics. That means these are essentially kind of diagrams that quantify what are all the forward and feedback loops that happen when you are doing something. For example, if China is going to tomorrow increase production, what is going to happen in the world, right? What is the dynamic of how that's going to go and transplant it or transform itself through the world? It has all kinds of effects. So there's a field of science called system dynamics, where experts come together and they say, well, this is the forward and feedback loops that are happening. So you can get very complicated diagrams. Now, what comes out of this diagram is the reward. So you input the actions, outcome the reward. One of the critical parts of this is the uncertainty. Of course, there's uncertainty in here, but there's uncertainty in the resources, right? So you could say you hear a lot on the news, like here all the time. Yesterday it was like there is a bonanza of lithium in the Imperial Valley of California, 70 billion. Well, we don't know this for sure. It's a resource. It's not a reserve. A reserve is an economically feasible, extractable material. So when you read the stuff in the newspaper, it's actually, there's no 70 billion there. There's zero there, right? So that means that you're going to have exploration actions or development actions that are going to allow you to reduce uncertainty, take something from a resource to reserve, but that is going to take time. That is not instantaneous either. Then you have mining, right? That's not instantaneous either, right? As I said, it takes a long time. So what we want to do with this AI is answer all kinds of questions, such as, should the United States start mining? When should the United States start mining? How much effort should we put in exploring, right? This is the problem in the United States. There is, if you go apply to the DOE, you'll get lots of grants in recycling and zero grants in exploring. I cannot get any funding from the US government. I get all my funding from companies because all the government is investing in here. So we can then answer that question and say, you have to really focus on this, otherwise you won't even get there. So this is kind of the stuff we're trying to answer with this.
Is there any chance per se that your model could be biased towards one word, or is your goal to, like, I guess, find a balance between all?
Yeah, that's the idea, is to find that balance. And this is the hard one here often, is that this is hard to quantify. Right? Now, in Australia, they've done a lot of work on this because Australia and Canada, they're mining countries, so they're very engaged with this. So we're working with the Australians, that is CSIRO is the Australian NSF, right? We're working with them in order, they have models for social license, and they know how this works, so that's a very important one.
Thank you.
Mm-hmm. Yes, there, yeah.
Just to follow up to what you just said, when you said there's no grants for exploration and mining in the U.S., can you elaborate on why that is?
Yeah, I mean, there's very little, if you want to do exploration, there's almost nothing that you can apply for. This is the fact.
But we have the reserves, right? It's just...
No, we don't have reserves at all. We have resources. So resources and reserves, right? So there's people always talk about this and say we have so much stuff in the United States. a lot of that is underexplored and underdefined, right? So this is a problem in the United States compared to Canada. That's why we're at the cobalt metals, we're only present in Canada. We have no presence in the United States. Number one, it's impossible to get permits, or it takes 4 years to get a permit. And then there's just not the kind of infrastructure for exploration, in particular, the USGS, which is the United States Geological Survey, which I'm going to start collaborating with. They've been tasked by Congress by 2030 to make an inventory of all the critical minerals, right? By 2030. And these people, if you look at, they're amazing people, amazing geologists, but there's only 10 people working on this problem for 50 minerals for the entire 50 United States of the United States. It's just, we are understaffed here. Who's doing mining engineering at Stanford, right? What schools do mining engineering? So you have Colorado School of Mines, you have Minnesota, you have Arizona, but that's it, right? So we are not doing anything in here because we're not educating and we're not having that. So that itself is already a problem. That's an educational problem. And this, of course, is, people say, well, mining, that's dirty, right? Well, oil is much dirtier, right? The carbon emissions of mining is fraction of a % of the carbon emissions of oil production. Right? So it's dirty, yes, but it's not nearly as dirty as oil and gas. Yeah.
Hi. Thanks a lot. It was very exciting. You mentioned Mark Jacobson in his book, and I'm quite happy that he's going to be my advisor here because I have some background in.
Okay. Yeah.
I was just wondering because I've seen quite some energy system models and then also integrated systems.
Yeah. Mm-hmm.
Your approach actually looks like perfectly suited for these kind of problems. Have you ever looked at these opportunities?
Yeah, no, that's a good. This is that, right? So what we are saying is that the integrated assessment models missing in a component, which is the information component, right? Because these are systems that you just, it's a scenario system, you let loose, right? And it's basically a forward model. It's a system dynamics plus databases plus this plus that, right? And you forward model it and you get that. That's not how the world works. In the future, you get information. That information, anybody's going to use that information, right? For some purpose. If you see that suddenly this particular energy system doesn't really work, you're going to replace it with something else, but we don't know that yet. So there's also information created. We have done a very small toy problem around this for lithium, where you had uncertainty in lithium resources and then you had mining of lithium. And so if you don't account for the information effect, you're going to mine deposits that are not mineable or non-economic. Because the scenario analysis doesn't account for the fact that at some point in the future, you will discover there is no lithium here, right? So in order to do that, then we saw that actually the CO2 we were measuring at the end was less than the CO2 that was measured through the scenarios because the system adapts itself. So if you just do a passive forward modeling, the CO2 you get at the end is likely an overshoot of the actual one because we are likely going to adapt here in the middle based on new information, new technologies, new things that are happening. So that's kind of where I'm standing on this integrated assessment models.
I have two quick ones, you don't have to answer both of them. One is about mining in the industry. Have you seen any impacts from the IRA on what people are saying? Mm-hmm. And the second question is a follow-up to the previous question, but other than integrated assessment models, do you think this framework could be applied to like capacity expansion models, thinking about what resources are built and the type?
Yeah, I don't know about the second one because I don't know about that. The IRA is a fantastic thing, right? It's definitely, what the IRA has done is not just in the United States, it's also outside the United States, right? Is that suddenly people want to invest in the United States for that. What it hasn't done, though, is solve the major problem for mining, which is the permitting and the social license to operate. It's not solved, right? So the land rights ownership issues in the United States are very complicated. Who's owning this land that you're sitting on, the mineral rights? And that has not been solved. Now, what is going on in Congress is a bill that says that you have to get the permitting decided in a year and a half. Because the problem in the United States is that it's so bureaucratic, it's just pushed from one department to another department, right? And every department says, I got 2 years. Right? And they're sitting constantly waiting for those permits to happen. So that's I think, the major bottleneck, not so much the science and the technology. Yeah, welcome.